This is section 9.2, inconsistent and dependent systems. So we're still talking about matrices here. We're just going to look at some situations that differ from the ones that we looked at in 9.1. So let's just recall what we looked at in 9.1. It's telling us here to solve the system using matrices, and then it talks about if there's no solution or if there are infinitely many solutions, which that's what we're looking at in this section. But this one actually does have a solution. So the first thing we're going to do is go ahead and write the system as a matrix. So here's our system. As a matrix, it's 1x, 2y, 0z, because there's no z there, equals 0. Then in the second row, we have 1x plus 3y plus 1z equals positive 1. And then in the third row, we have negative 4x minus 1y minus 1z equals negative 25. And so all of those came from the coefficients in front of x, y, and z, and then that constant on the other side of the equal sign. So that is what we'll put in our calculator. F3 for matrix. This is a 3x4, so I don't have to rearrange the order. I just have to press execute to open it up. I'm going to enter that in. Okay, check it out. Make sure all those numbers are correct. 1, 1, negative 4, 2, 3, negative 1, 0, 1, negative 1, and 0, 1, negative 5. Okay, so now let me exit out. I have my matrix A set up. Remember here, we're going to now press Option, F2 for matrix, F6 to arrow over to the right for more options, and then F5 to get the command ref. Then we'll press Shift 2 to get matrix, alpha A. So now we're commanding the calculator to solve for x, y, and z. So it gives us this 6, negative 3, and 4. So we see that down here. Remember, if I was now to write this matrix back as a system, this would be 1x equals 6, 1y equals negative 3, and 1z equals 4. So there is a solution to this system, and it's 6, negative 3, and positive 4. Okay, so that's how it looks when there's a solution. But now we're going to look at where the system is dependent and there are infinitely many solutions, or there are no solutions. So as a matrix, this is what we would enter in. 9, 20, 8, 10, 4, 9, 5, negative 6, 1, 2, negative 2, and 6. And I just got that from these coefficients going across and the constants on the other side of the equal sign. All right, gonna enter it into the calculator. Okay, so I entered that matrix in. Let's exit out. Again, if you're trying to figure out how to get to ref, I would definitely check out video for 9.1 because we go through that a lot slower. Okay, so this is what we get. Let's match it up with this. Okay, so this is what I got. Now, let's go ahead and translate this matrix back into a system. So I would have x minus 28z equals 0. I would have y plus 13z equals 0. And then notice that I have zeros in front of all my coefficients. So just 0 on the left side equals 1. That's the row that I'm interested in, because that is not a true statement, right? And because that's not a true statement, then this would be that no solution option. There is no combination of an x value, a y value, and a z value that can make this system work. So no solution. Okay, and then on the other end of the spectrum, so let's talk about what we would enter this in as the matrix. -1, +1, +1, -5. Again, just getting that from these coefficients here. -1, 5, -19, -33, 7, -2, -32, and 0. Okay, so we would do the same thing we did on the last one, where we go ahead and save this in as matrix A, and then we go back to the main screen and put ref matrix A, and this is what it's going to kick out. Okay, so again, if we were to translate this back into a system, that's a Z, sorry. We have x minus 6z equals -2, y minus 5z equals -7, and 0 equals 0. That third row is what I'm focusing on, because that makes a true statement, right? 0, unlike the last one that said 0 equals 1, or 0 equals anything besides 0, if it's an untrue statement, then there's no solution. Okay, and we'll talk about how that actually looks in an example. But if it's 0 equals 0 and it's a true statement, then we have infinitely many solutions. And it means that the system is dependent. So two extremes, right? Either, well, let's talk about that first example. Either we come out with a solution, right? And we have a value for x, a value for y, and a value for z. Or we have that untrue statement in the last row, and that means there's no solution. There's no 3 values you can plug in for x, y, and z that could match up for all those equations. Or we have this third option where we have this true statement in the third row, 0 equals 0, and that means that it's infinitely many solutions and it's a dependent system. As a matrix, we would enter this in as 1, -1, 1, 6, 5, 1, -1, and 0. And if you don't enter in that third row, then you will not get a third row here. And so that might confuse you a little bit. Now remember, there's 3 variables, and so you'll want to put in that third row. If not, you will not get that output there. Also, just looking at this, if I was to use the addition method here, look what happens. Those 0 out, I get 6x equals 6, x equals 1, and look over here. Sure enough, x equals 1. Right? So just to see the connection there, but we could enter this into our calculator, and this is what would pop out. So this true statement right here, which you could even see this over here, but this true statement here would make this infinitely many solutions. But be careful. So let me show you on the calculator. If I only entered a 2x4, so I showed it on the calculator. If I only entered in what was here and I didn't enter in that third row, then when I do RF matrix A, it's only going to give me 2 rows here, okay? Now, this is going to be useful in the following problems that we're going to work with, but just make sure that you understand if you're missing that third row, that's why. Right here, we can actually express it a certain way. So let me just talk about that briefly. So if we did y b1z equals -5. So I have x equals 1, and then here I have y minus z equals -5. If I wanted to express what y is equal to, I could always express this, right? X will always be 1, and then y will be equal to whatever z is, -5. So z, we could pick any value for z, right? No matter what, x will be 1, and then y will be whatever z is, -5. So let's actually look at the problem. I think maybe it'll make more sense once we see this, because this problem sometimes gets people. So let's talk about it. Okay, so it says the figure on the right shows the intersections of 3 one-way streets. To keep traffic moving, the number of cars per minute entering an intersection must equal the number exiting that intersection. Write an equation for intersection I2 that keeps traffic moving. Okay, so here's I2. So they said, look, the number of cars coming in an intersection that are entering an intersection have to be equivalent to the number of cars going out. So let's say cars coming in has to equal cars going out. And actually, you know what? We're going to put that in a different color so we could identify what that is. Okay, so in blue, cars going in to I2. We have cars coming in right there, right? So they don't give me a numeric value, but they give me a variable representing a value, so z. And then where else do we have cars coming in? We have cars coming in here as well, so 7 cars. So we have 7 plus z coming in per minute, and then going out we have 5 cars per minute, and then also we have x number of cars coming out per minute. So 5 plus x coming out per minute. Okay, so looking at the answer choices, they have x plus z equals 7 plus 5. Nope, that's not going to work. Z equals x plus 12. Even if I solve for z in this equation that I have down here, I would subtract 7 to get z by itself, and that would actually give me a -2 on the right. So that's not going to be it. They have z plus 5 equals x plus 7. Super tricky because they mixed around the variables with the constants there, so be careful. Or z plus 7. So this right here would not be right, because if I had z on the same side as 5, I would subtract 5 over here and I'd actually have z minus 5, and then I would do the same thing with the 7 to get on the other side, right? So be careful of that. But here, z plus 7, well, I can write that mixed around because it's on one side. So 7 plus z is the same thing as z plus 7, and then x plus 5 is the same thing as 5 plus x, so it'll be D. Okay, and then this one right here. So this is the one where we're going to use expressing a variable in regards to another variable. So what we were talking about before we actually went to this last problem. It says the figure on the right shows the intersections of 3 one-way streets. it's telling us to use that Gaussian elimination method. That's the method that they will show you when you go and ask for help in MyMathLab. But remember, that method will drive you insane. You can try it, but we have a more efficient way, I believe, of doing it. So it says solve the system of equations that models this situation. So they go ahead and they give us what we were looking at before, right? So right here, they were asking us to find an equation to represent intersection 2. Well, here, they actually give us the equations to represent each of the intersections, right? Cars coming in, cars going out. And they want us to solve the system. So this is a system. They want us to solve the system for this. So the very first thing I'm going to do is write this in standard form, because once I get it in standard form, then I can go ahead and enter it into the matrix and then solve for it, right? So let's take this first one. I'm going to subtract 8 from both sides. So I have x equals y plus 4, and then I'm going to subtract y from both sides, and I'm going to bring it down here. X minus y equals 4. Okay? And then for my second one, I'm going to subtract 15 from both sides. Let me move over here. I have z equals x minus 9. I was going to say 11, went the wrong way. Minus 9. And then I'm going to subtract x from both sides so that I have negative x plus z equals negative 9. Okay, and then for this last one, I'm going to subtract 18 from both sides. Then I have y equals z plus 5, and then subtract z from both sides. So I have y minus z equals 5. Okay, so all I did was manipulate each of those equations that were given to me so that they're in standard form. So when I go to write this in my matrix, I'm going to go ahead and take my coefficients. So I have, in my first equation, I have 1x minus 1y, there's no z, equals 4. Then I have negative 1x, there's no y, plus 1z equals negative 9. Then I have no x in my third equation, plus 1y minus 1z equals 5. Okay, let's go ahead and plug that into the calculator. Okay, F3 for matrix. This is a 3 by 4. All right, check my numbers. 1, negative 1, 0, negative 1, 0, 1, 0, 1, negative 1, 4, negative 9, and 5. Let's exit out. Go ahead and press Option. F2 for matrix, F6 for more options, and then F5 for RF. Shift 2 for matrix, and Alpha A. Okay, so look at that last row. We have 0 equals 0. That means that there's infinitely many solutions, right? But notice that on option B, they have a box for y and for x and y, but not one for z, because z is going to be consistent, whatever that value is going to be, then we're going to say, okay, well, in regards to that, what is x and what will y be? So let's go ahead and write this down. Okay, so I copied that down from what the calculator output was. So what we have here is x minus z equals 9. Remember, this is x, y, z, and then that's our constant. Then I have y minus z equals 5. Z is my constant here. There are infinitely many solutions. Z is my constant there though, right? So whatever z is, now I needed to be able to express x and y in reference to z. So if I was to solve for x here, in that first equation, I would add z to both sides, and I would get x equals z plus 9. So that's what I will put in here, because that is what x is equivalent to. And then for y, go ahead and solve for y like you normally would. And you get y equals z plus 5. And that is what you will put in for y. So what this is saying is whatever value z is in this setup, whatever that value is, then x would have to be 9 more than that value, and y would have to be 5 more than that value. Okay, so when you get to this problem, just make sure that you understand, okay, it's infinitely many solutions, but now I need to express x and y. I still solve for them the same way, but now I'm expressing them in reference to z.